Thanks everyone so much for joining. The science team has been pretty excited putting together this presentation. I know it's been a request and a long time coming to really talk about the science and give a deep dive and a perspective on what we've been working on. Giselle, I know, has put together a presentation in the past reviewing some of this, and I think it's just really good as we move forward with this methodology and upgrading this Grasslands methodology to really give a background and understanding of what we're working on. So the goal of this presentation is really focused on not only providing insight on the methodology itself, but also a little bit of background on remote sensing, why we use remote sensing, really understanding the basis of where we're coming from on the science team. So to start us off, just a brief overview in terms of what we're going to talk about today. Like I said, I think it's really important to set the stage, understanding some of the basic terminology we'll talk about when we discuss our methodology, of remote sensing, some of the terms we'll be using. Then we'll move on. Sam's going to zoom in and talk about our Grasslands methodology specifically, the steps we're taking to convert, Landsat or Sentinel-2 imagery to calculate soil organic carbon and quantify carbon sequestration. Then we'll contextualize this with an example of Wilmot and how we did this with the Wilmot farm. We'll briefly touch a little bit on the co-benefits and the methodology we use there to calculate and quantify the co-benefits we align with each project. And then finally, as Sarah mentioned, we will have Giselle talk a little bit about the frequently asked questions and then really provide a platform to just ask any questions you have of us in terms of the science itself, in terms of remote sensing or the CarbonPlus methodology. So that's the overview of what we're going to talk about. And really just to dive in, like I mentioned, I think it's really important to understand some of the basics of remote sensing before we dive into the methodology itself. So again, this is a very brief overview, but some of the key points, at least I consider important as we discuss remote sensing and satellite imagery. So on the left, when we're talking about satellite imagery, there's two metrics we often discuss. And the first is spatial resolution. And really the essence of this, you can see in the visual down at the bottom. This is in relation when we're talking about spatial resolution of the size of a pixel. So when we're talking about satellite imagery, we're talking about images coming in, and you can think just like a picture, you're talking about how detailed, coarse the pixel sizes are. So you can see we have different pixel sizes in terms of resolution. On the left, you can see 30 meters, in the middle 5 meters, and on the right 1 meter. And you can see the pixel output depending on the pixel size and how that changes and reflects. So really what I'll talk about in the next slide in terms of the satellites we're using. But as you can see, the more detailed, the lower the pixel size, the better outputs in terms of reflecting what's actually happening on the landscape. So that's spatial resolution. When we talk about spatial resolution, we're just talking about the size of the pixel. And then secondly, temporal resolution. And this is simply just the time between images. So when satellites are rotating around the Earth, they're taking, a snapshot of a certain location in space. And then either they will loop back around or a dual satellite will come and take a snapshot of that same location. So when we're talking about, say, temporal resolution of 5 days, we're essentially saying that for the satellites that we use, we're going to be getting different snapshots every 5 days. So that's kind of like the revisit time. So that's when we're talking about temporal resolution. That's what we're referencing. And then when moving over to the right, this is a very basic breakdown of remote sensing, and when we talk about spectral bands. So you might hear us when Sam goes through our methodology, talking about aligning different spectral bands to soil organic carbon levels. And when we're talking about spectral bands, what we're really talking about is the alignment to different wavelengths within the electromagnetic spectrum. So you can see here on the top just a basic infographic on the electromagnetic spectrum. And then down below, you can see Sentinel-2. So I'll talk about this in the next slide, but that's the sensor, the satellite we're using. And you can see how different bands are aligning to different wavelengths. So you can see, visible light, we have a blue, a green, and a red band. And those are just 3 of the bands that Sentinel-2 picks up. But we also have bands outside of the visible light spectrum. So you're talking about near infrared or shortwave infrared. So when we're talking about different bands, we're just talking about these different ranges within the electromagnetic spectrum that we're able to pick up. So that's a little bit of background. One other thing I wanted to touch on is Sentinel-2. So all of our analysis thus far in terms of our CarbonPlus grassland methodology is using Sentinel-2 multispectral instrument. And this is a quick breakdown of some of the specifications of this satellite. So first, it's a European Space Agency satellite. In terms of data set availability, we're looking at 2017 onward. So this is really important when we talk about onboarding projects with historical soil sampling. Really, we are limited in terms of temporal availability by the data set. So that's why for both Wilmot and Woodburn, even though they may have samples that are prior to 2017, we're really starting with 2017 due to the basis of that's the earliest we can get Sentinel images. So that's a really important metric as we onboard projects to take note of. And then again, temporal resolution, and again, that's that revisit time. We're looking about every 5 days. Spatial resolution, we're looking 10 to 60 meter resolution. Most of the bands we use are actually within that 10 meter resolution framework. And then finally, within Sentinel, as you saw in that previous little visual, there's 13 spectral bands that it takes for each of its images. So moving forward in terms of what can remote sensing tell us, why we use remote sensing, why it's so beneficial. So not only do we have that background in terms of the different bands that we can use, we can also combine these bands to calculate indices. And what we're really talking about, I think a great example of this, and probably the most famous and commonly known indice, is NDVI, and this stands for the Normalized Difference Vegetation Index. It's a basic index on vegetation health. And I think it's really important just to understand kind of the basics of what's happening here. So on the left is a nice little infographic, and you can see that in terms of healthy vegetation, it is reflecting about 50% of the near infrared wavelength, but absorbing a lot more of that red light coming in. So it's not reflecting that much back. But for a stressed vegetation or a stressed plant, you can see there's a difference. So it's actually reflecting back more of that red light and absorbing a little bit more of that near infrared. And then we can incorporate this into an equation you can see down at the bottom, which will give us a final score of NDVI. And moving to the right, you can see how that reflects in terms of ranges. So you can see on the right, if you're getting kind of an NDVI value that's 0.66 to 1, you can be considering that pretty healthy vegetation or a healthy plant. And then some of the lower values like 0 to 0.33 is an unhealthy plant. So I just think we use indices not only in some of our quantifications for soil carbon, but also for our co-benefit of ecosystem health. So I figured it was worth touching on. Down at the bottom, I just listed some other ecosystem indicators that we can use and that are really important. So you can look at fire impacted areas, or you can look at the water content held in the soil, bare soil indices, or even forest health. So that's just a basic background on remote sensing indices and how we use those. And finally, the last thing I wanted to touch on before we really dive into the meat of our actual methodology is talking about the benefit of remote sensing. So really the basis of what we're doing with remote sensing in tracking changes in carbon to calculate these carbon sequestration metrics is based on time series assessment. So I really love this visual on the right. I think it really encompasses the benefit and the advantage of using remote sensing in ecosystem health and carbon change analysis. So you can see that up on the left, we're pulling out an image for a certain region. And within that image, because the benefit of satellite imagery, it's being revisited every so often. So you have a full stack of images that you can then look across time or look back in time to look at the change. So what it's showing here in the middle is just looking at a single pixel within that image, and you can see how that changes over time and see how the values are changing to reflect changes in the landscape. And then from there, what you can actually do is pull out these spectral values and then look at how is this changing over time? And you can see a drop here and relate that to, okay, it looks like between the years of 2000 to 2005, something happened. We can look into there and see how that changes. You can detect deforestation, increased vegetation. Just one of the big advantages of remote sensing analysis. And for us, we're looking at changes in percent soil organic carbon. So again, looking at how is that changing over time, going back to 2017, at each pixel, how much soil organic carbon are we picking up using our remote sensing indicators? And again, like I mentioned, we're also using this to look at changes in ecosystem health. So that's just one of the breakdowns of why remote sensing is so important, why we've decided to use it, and how it's really cutting edge in terms of tracking change over time and looking at changes in soil organic carbon. So now I'll pass it off, I believe. Now I'll pass it off to Giselle, and she's going to talk a little bit about the state of the art of remote sensing for soil organic carbon in this realm.
Yeah, thanks, Sophia. So I just wanted to share a little bit of context here, given that past year I participated in a work with Dan Kane and Patrick Lawrence for the Ecosystem Services Market Consortium. And it was targeted to analyze the different methods for measuring soil organic carbon and the state of the art of all the tools that could be used. And we created a report specifically for remote sensing. So I wanted to share the main outcomes here briefly. Overall, I wanted to show that, for instance, the growth of publications is remarkable in the past 10 years. So you can see there that all the, here there are some publications related to agriculture, and you can see the frequency has increased in the past 5 years mostly. And if we narrow down that into only the remote sensing dedicated to soil organic carbon, it just goes into maybe 65 reviews and papers that we could find related just in the five last years, I would say. Then on the right, I wanted to show that there's also a coherence of this related to the increasing amount of satellites that are going out there, that have been launched and are also going to be, increasing also the accuracy. So you can see there the spatial resolution in the y-axis, and you can see that has increased, the spatial resolution has been narrowed down into a few meters or sub-meters in the last years. Next. Okay, and here I wanted to show first on the left, you can see I marked in red the Sentinel. In the x-axis, we graphicated the resolution. And then in the y, you have the error. This is a metric, the normalized error from the measurements on soil organic carbon from all the papers that we reviewed. And you can see that Sentinel is quite well positioned because it has moderate to good resolution, but it has a very good accuracy, a very small error as compared to other satellites, and also is free and open source. And then on the right, what I wanted to show is, and Sam and Sophia will get into weeds with the methodology, and we'll show that we are using several machine learning algorithms. And so the ones that we are using for the methodology that they will explain now are mostly random forest, and we are going to start with support vector machines, which are the ones I highlighted. And you can see there's a wide interval of results according to the error that, or the accuracy. And that depends also on the user experience, you know, the how well people are formed or capable of getting good results too, because this is a very nascent, as I showed before, nascent technology. So, but the good thing is that you can see from the purple one, which is the random forest, that's the one we are using. If you are good at it, you could get really good results. And this is again based on reports on soil organic carbon measured by remote sensing. It's not from a broader spectrum. It's targeted to remote sensing for soil organic carbon. Okay, next slide. I think it's turn for Sam.
Cool. So thanks guys for providing a nice background on remote sensing. And I'm gonna dig a little bit more into our grasslands methodology and how we convert these soil samples and remote sensing data into final soil organic carbon stocks that we can later sell as carbon credits. So there are two key players in quantifying soil organic carbon stocks, and those would be the land manager and the monitor. The land manager is going to be providing the soil samples, which we use as ground truth data, and then the monitor is going to take those soil samples, combine them with remote sensing data, mainly satellite imagery, and then do some statistical modeling to make predictions, and then ultimately turn those into soil organic carbon stocks. So kind of going left to right, and Sophia did a really good job making this slide because I think it really, clarifies how we go about doing this. So we start with the soil sampling. So when we adopt a project, we are going to look at the project area, which is highlighted in green. This is an example of Wilmot. And depending on the size of the farm, we are going to tell the land manager, we need X amount of soil samples to accurately predict soil carbon on your farm. Every year, the land manager is going to take soil samples, which are going to include soil organic carbon, bulk density, and other soil health metrics. And then they're going to take them to a lab, and then that lab is going to analyze them and then provide the monitor, in this scenario, us, with the data that we can use to start the modeling. So that kind of takes care of that first box. And then moving into the second one, this like pre-processing step would be kind of integration of remote sensing data and combining that with the ground truth soil carbon data to make a data set we can model with. So we're mainly focused on using satellite imagery. We will take a set of satellite images taken within about a month or 2 months of the soil sampling date. We'll do some pre-processing to just clip those satellite images to our study area, make sure that there's no clouds or atmospheric irregularities in those images to provide like the best data set for analysis. And then we'll combine those, the different bands into a data set with soil carbon. So like Sophia mentioned earlier, when a satellite image is taken, you're not just getting the visible wavelengths, but you're also getting infrared or gamma wavelengths. And then we combine all of those different, what we call bands, into a single data set. This is also a section where we might incorporate other remote sensing data, such as percent clay or percent silt found in the soil. We can also incorporate elevation data of how high the different soil samples are, or things like the topographic wetness index, which might tell you how much water content is found in the soil at different areas. And so we kind of package all this up with soil carbon and create a data set that we can now take into our statistical modeling. I think Giselle mentioned that we are using kind of 2 different statistical modeling methods. The first is linear and power regression, and the second is more machine learning models. So in our original methodology, we were focused on using linear and power regression, which would just compare soil organic carbon to a single band, let's say the red band or the near infrared band, and see if there was a correlation that fit the data really well. And if there was, we would later turn that into percent soil organic carbon map. But recently, and especially as we move on to more complex project areas, such as Kavan, which is one of our impact ag projects, we're starting to use more machine learning models, which allow us to incorporate a variety of data. So rather than looking at one band, we can look at all the bands. We could also incorporate those like elevation and soil health metrics into that as well. And once we fit a model that we find to be accurate, we'll use that to predict soil carbon. I think you can go to the next slide, Sophia. So to provide you guys with a more concrete example, this is the Wilmot project, which was our case study. So on the left, you can see the soil sample locations overlaid on the project area. After combining those with the satellite images, we created these percent soil organic carbon maps. The percent soil organic carbon we were finding range from about 1% to 7% found in the soil. And so the advantage of using this like remote sensing data is that for each one of these like 10 by 10 meter pixels, we can predict a different soil organic carbon value. So it is a lot more precise than more traditional methods, which might just do what's called like area weighted extrapolation and use like a single value to interpolate a much larger area. So once we create those soil organic carbon maps, we can calculate our final stocks, which to do that, you need the percent soil organic carbon, the bulk density or the density of the soil, because some areas might be denser and contain more soil carbon than others, and then the soil depth. It's important to note that we only predict the soil depth of the soil samples. So if the farmer collected soil samples at a 5 centimeter depth, we would predict just those first 5 centimeters of soil, but then typically we're doing 10 to 15 if they are able to collect those. And then from there, we can calculate our final soil organic carbon stocks. And so that is on the right, and you can see how the soil carbons varies across the farm. These are just parcels of the different plots of land that the land manager has chosen to divvy up for grazing practices. So you can see that in some areas, we're seeing much higher soil carbon than others. You can go to the next slide, Sophia. And then to calculate CO2 equivalents or creditable carbon credits, we will compare our stocks between years. So we have our stocks from 2019, and we'll compare those to the stocks from 2017. If there's a net gain, then those are creditable carbon stocks. Before we generate that final number, we're going to reduce the animal emissions. So because there are cattle on farm emitting methane, among other gases, we're going to deduct that from our carbon credits, and then also work in the model uncertainty. So all these statistical models that we're using to predict soil carbon might have different levels of uncertainty, and we want to make sure we account for that because we're monetizing like these soil carbon stocks. And then finally, to generate our final number, we multiply it by a factor of 3.67 because there's a difference between measured soil carbon or the soil carbon found in the soil and the greenhouse gas equivalent carbon, which is by this factor of 3.67. And then from there, we'll get our final number and then do our buffer pool and other deductions to get our final number. So, oh yeah, and then I guess what also distinguishes our methodology from other methodologies in the field right now is that we are not just measuring carbon, but we're also measuring other like ecosystem health indicators and metrics of the kind of just like how the farm is being managed. So the three that we focus on are ecosystem health indicators, which help show the farm, I guess like the vigor and the resilience of the plants and just landscape of the farm. The soil health indicators. So rather than measuring just soil carbon, we're also going to be measuring things like pH and the amount of nitrogen in the soil, just to make sure that there are healthy levels and that the land management practices are improving on a wide variety rather than just sequestering carbon. And then finally, animal welfare, which is just how the animals are being treated. So you can go to the next slide. So I guess going to the ecosystem health indicators, one of the main ones that we focus on would be ecosystem resilience and ecosystem vigor. So for ecosystem resilience, we want to make sure that we're actually seeing like a good plant coverage across these grasslands over time. So what we do is we compare the grass cover within the farm to the area outside of the farm. So this is an image of the Cavan location, and you can see highlighted in black is the Cavan property boundary, and then we have this 30-kilometer buffer around. And so what we're doing is we're comparing the amount of exposed soil within the farm to the amount of exposed soil outside of the farm, and we're essentially taking averages and seeing if we're getting a good plant cover like across the entire farm. Other things that we might look at were what Sophia talked about earlier, which is the NDVI, or a general metric of just overall plant health. So we're comparing the plant health within the farm to the surrounding area and seeing if it's improving over time or not. And then we also might be looking at forest cover, which is another one of our metrics. So you can go to the next slide. Sweet.
Cool. Okay, and then a few other things we can touch on really briefly that are less remote sensing intensive, but just some things that we are considering in our co-benefits. Like Sam mentioned, the first being soil health indicators. And yeah, as Sam mentioned, when they're pulling these soil cores and sending them to the lab, they're getting values for, say, pH or nitrogen or phosphorus. And what we do here for the soil health co-benefit is we're looking at local metrics in terms of what is considered optimal in the region. And then from there, we create a ranking in terms of the number of samples they pulled from that farm, how many of them fall within, say, the optimal range versus the moderate range versus the poor range. And then we have a weighted ranking system where we combine all those values and all those metrics to get a final score of, say it's very excellent, meaning most of the metrics were falling into the optimal range, or maybe moderate, where there could be some improvement in terms of the overall soil health. So that's for the soil health co-benefit. And then as Sam mentioned, the second one we're talking about is animal welfare, which is pretty straightforward. So again, we're looking at local metrics that they use to look at animal welfare. For example, for the Wilmot, since we're looking in New South Wales, we're using a standard metrics from the Australian government in terms of cattle ranches. So some of the examples is we have a whole list of animal welfare metrics to look at. So say access to feed and water or risk management. Are the facilities cleaned, and do they have good access to food and water? Are they healthy? So what we do is we look at all these different metrics and discuss with the landowner which ones are being fulfilled, which ones might need improvement, and again, are getting a final score there. So those are the two other ways, the two other co-benefits that we're incorporating into the final reports for each of these projects. So now we'll turn it over to Giselle, who's we're gonna move out a little bit and talk about some of the frequently asked questions, and then open the floor to some general questions.
Yeah, so I created a list with some of the questions that have been asked to the science team back in December and through all this process. But I will tackle maybe the first three and then open for more questions. If you will to review this and see if you want to ask some of the following ones. I just don't want to spend a whole lot talking myself. I would rather listen to your questions now. So first, I will answer the first one. How do we calculate uncertainty? Because given the design of our credits, the uncertainty implies that we do a discount. And so it's important not only for transparency and credibility, but it's also important for the final amount of credits that we issue. So maybe I think next one is maybe explaining that. Yeah. So here I have like a schema of the whole process, starting well, and the resolution is not very good. But first of all, we estimate the uncertainty from the soil organic carbon percentage estimation based on either the results from the linear or power regression, as Sam explained that we were using until now, or based on the estimated accuracy from the machine learning algorithms. So that's one source of uncertainty. Given that the way we designed the methodology, once you get that uncertainty, you're including everything from the sampling method they used, any uncertainty from the sample collection, any uncertainty from the lab will be included here. Just because this is like the overall uncertainty at the end of the process, where you compare the actual values with the values from the map that is created. And then, as we showed, we need to incorporate the bulk density in order to estimate the final uncertainty for the carbon stocks, because we are going to use it in the equation for the final stocks. So that's another source of uncertainty. And the way we are doing it right now, for instance, we were using pedotransfer functions, and we were comparing the real values from the sampled years to the estimated values from the pedotransfer functions. Pedotransfer functions are just equations based on bibliography from other research in the area or in similar ecoregions, where they linked the soil organic carbon percentage, in this case, with something else. In this case, they linked the soil organic carbon percentage with the bulk density, and so you can estimate only by having the soil organic carbon percentage or the soil carbon percentage and the silt content of the soil, or it could be about having like the clay content or many parameters that you could get from the lab samples. As we do have that information, but we don't have information for all the years for the bulk density, then we estimate the bulk density map based on the things that we do have from the years that we just don't have samples from the soil, from the ground with the bulk density. Okay, if you go back to questions, yeah. So another question is related to how do we select the baseline? And this is not, this is a very relevant question. I would say that so far it has been, given that we only run Wilmot and Woodburn we completed only those studies. The way we were doing that is just relying on the information we had from the ground, and we were looking at the correlations and finding and measuring the accuracy. And if the method was good enough, then we could use that year and the data from that year. Also, we are only going back in time until 2017, because that's the moment where the Sentinel image, the first images are available, because they launched the Sentinel satellite that year. We could be using, for instance, Landsat from previous years, but then the resolution is lower and the spectral resolution also. And that's why we are relying on the Sentinel to get a better accuracy. So we don't have, definitely we need to create some rule of decision here. And it's something that the science team will be putting heads on in the coming weeks. And then the third question I wanted to answer is, why don't we use dynamic baselines instead of a static baseline? So the way we are doing it right now is we have 1 year is the starting year where we find a correlation. That could be, for instance, for Wilmot, it was 2017. And then we measured the soil organic carbon percentages, the bulk density, blah, blah, and we got the stocks from 2018 and 19. And so we just subtracted, considering the first year, which is 2017, as a baseline, we subtracted that from the rest of the years. And so just by applying like a simple calculation, we could get the final stocks as the difference between the baseline and the final stocks. The dynamic baseline, which is what NORI uses, so far dynamic baselines are used, for instance, the Descent model, which is within the Comet farm, can create a dynamic baseline, which is the modelization of the soil organic carbon stocks according to previous information from historical data. And they are often only developed for more traditional, not regenerative practices, but more traditional. And in the case of Comet, only or most of it for cropland. And so they they model 10 years of climate. They run the models for that those variabilities in the climate, and with that they get the stocks that would be measured in that piece of land if they are applying certain practice. So with those 10 years, they move forward and they just use that database of fake modeled data, I would say, modeled data. And every new year, they quantify the carbon, again, only based on models, because they just extract inputs from the farmers, and they model the soil organic carbon with that. They consider the actual climate, and they refer to the soil organic carbon that would be the stock according to the traditional management. And so with that, they get a difference from the carbon they are measuring as compared to the output of a model whose input has been the traditional management instead of the actual management. Again, this is all why we're not doing this, because this seems to be better in the sense that you are accounting for the additionality, and so you're only measuring what's the carbon sequestration apart from the natural variability of the carbon. The reason why we didn't overcomplicate things is just because we need to develop a methodology for this in order to couple this with remote sensing somehow. So this will be in our next discussions for sure, but it's something that will be, I would say, longer term improvement of the methodology. It's not simple to solve, and only using models, I wouldn't recommend that, as any model like Decent has at least a 0.5 uncertainty. That's like the best uncertainty you can find in bibliography for any of these models, based on the comparison of the parameters at regional scales, not at field scale. So when you look at field scale accuracy, they go down, they drop a lot the accuracy. So we don't want to be modeling and comparing stocks to something that has 70% error or more. Okay. So I think with that, I will open for questions.